All right. Hello, everybody. I'm Jinhua Zhao, Professor of Cities and Transportation at MIT. This is the MIT Mobility Forum. Today, we have a very special occasion. We'd like to celebrate the MIT Eva Roos PhD Dissertation Award. This year, we have one winner and two honorary mentions. I invite all three of them to join us to really share with us their highlight of the research. Right. The Roos award is really generously contributed by Professor Dan Roos and his wife, Eva Roos, to support encouraging students to get into the field of transportation. And we set up this award to select among all disciplines across the MIT from any department, where, as long as the topic focuses on transportation or mobility broadly defined in any modes of transportation, any technology, policy, behavior, any aspect of transportation, right? So each year we gather this a lot of applicants, a nomination from many professors, and we set up a selection committee and review them. So for this year, I would like to thank Professor Amadeo Aldoni, Professor Alex Jaculette, joining me to form the selection committee. And also thank Heather from Dean's of Engineers Office for hosting this award at the Dean's office there. So this year, I'm really glad to announce that we have the winner. Let me project the slide so people can see the name exactly, right? So this Dan Eva Roos prize. And also I have to mention that these prior years in 2018, Dr. Gabriel Krindler won the award with the 3 essays on the economic urban transportation. And in 2021, Dr. Shenghao Wang won the award with the Deep Neural Network for Choice Analysis, right? So for this year, we have the Professor Aldoni, Professor Jaculette, and myself as the selection chair. And we actually shortlisted 5 student theses. I also tried to announce their name: Angela, Han Zhang, Baichuan, Rounaq, and Karthik. Among this, we selected 3. Rounaq Basu and Karthik Gopalakrishnan won the award with an honorable mention. And the final winner is Dr. Baichuan on the topic of towards a resilient public transportation system, effect monitoring and control under the service disruption. Right. So that's the 3 students and their presentation. But before I invite each of them to give a 10-minute presentation, I do want to invite each of them to say a few words about when did you come to MIT, when you graduate, who do you work with, why do you choose your topic of this research, and also where are you now, right? We are contributing to society in different capacity on this, right? So maybe I'll start with Rounaq, then Karthik, and then Baichuan. Rounaq, please.
Thanks, Jinhua and Bhuvan and the rest of the MMI gang for having me. My name is Rounaq Basu. I came to MIT for grad school in 2016, graduated with 2 masters and a PhD 6 years later in 2022. I had the pleasure and privilege of working with Joe Ferreira, Chris Zegras, Andres Yatsuk, who may be on this call. I've seen Joe certainly. Joe served as my PhD supervisor. Chris and Andres were committee members, and then I continued working with Andres as a postdoc after graduation. Earlier this year, wanting to connect my research better to planning practice, I started working at the Boston Region Metropolitan Planning Organization as the manager of multimodal planning and design, where I'm currently trying to improve my applied transportation planning work and balancing academic research at the same time. Thank you.
Thank you, Rounaq. Karthik?
Hi, everyone. Thank you so much for having me here. It's definitely an honor and a pleasure. So my name is Karthik Gopalakrishnan. I came to MIT in 2014 for a master's in aeronautics and astronautics. Loved the place and then stayed on for a PhD and graduated in 2021. After that, I was a postdoc at Stanford for a couple of years. And right now, I'm working at Tesla, where I'm working on navigation and routing problems for electric vehicles. At MIT, I was in the Dynamo lab, which was headed by Professor Hamsa Balakrishnan, and she was my advisor as well.
Great, thank you. Baichuan?
Cool. Thanks. Thanks for having me there, and it's my great honor to be awarded the award. And thanks Dan Roos and Eva Roos for the support. I came to MIT in 2018, and graduated with a PhD in transportation in 2022. I also got 2 master's degrees, one computer science, one transportation at MIT. During my time at MIT, I worked in GTL Urban Mobility Lab, and Professor Jinhua Zhao is my advisor. I also have another advisor from Northeastern, Professor Harris Christophorus. During my time at MIT, majorly worked on public transit systems. And now I'm in West Coast, working at the rideshare company Lyft. I'm a research scientist at Lyft, working on the real-time driver incentive design. Yeah.
Great, thank you. Yeah, so we for this hour, we put it to several rounds. The first round, each of the 3 will present their research 10 minutes each, really focus on the key kind of highlight and finding of this, right? The second round, I would encourage between the 3 student and panelists have a conversation with themselves, like commenting on each other's research and raising questions. And the third round, Baichuan will curate the questions from the audience through the chat. Right. Again, in this forum, we really want to reinforce the norm, which is everybody contribute an idea. Right. You can type it into the chat, either a comment or question to any of the 3 presenters today. And lastly, I'll reserve the last 2 minutes to Professor Dan Roos and Eva Roos to say a few remarks about this year's award and the student. Thank you again for Eva and Dan for really empowering the student and make this happen. So without further ado, let me invite Baichuan to start the presentation, please.
Yeah, I'm sharing the slide now. Let me know if you can see it.
Yes, if you do the slide, yeah.
Cool. Okay, yeah, let's get started. As you already know, like my thesis topic is toward resilient transportation system application to public transit. I modified the title a little bit to cover more broader topics in transportation system as a whole. Yeah, before I talk about my thesis contents, I want people think about the potential shifts of the research paradigm in transportation fields. People usually work on transportation field in like predictions, operation, control tasks. But when you think about this task, most of previous studies usually assume a normal situations for prediction or all these tasks. But the what never works as expected. As like Professor Jones said, uncertainty is only uncertainty there is. So this various unpredictable instances and disturbances happen every day. And what I want to argue here is like abnormal is the actual normal of the world. So if you think about it in this way, there should be a shift of transportation research paradigm from certain and normal to uncertain and abnormal. And to deal with abnormal, like resilience is a way to embrace uncertainties. The definition of resilience is the ability of the system to cope with unplanned incidents and disruptions. And before aiming to design a resilient system, we expect the system to be able to embrace uncertainties and protect the system's functionality under this instance. So at this study, we select public transit as a case study. It's a backbone of the transportation system. We aim to develop a resilient transportation system in 2 different important tasks. One is monitoring and another control. So the major objectives will be understand the impact of unplanned incidents on public transit system and design mitigating strategies to relieve the incident impacts. So for the first understanding task, let's first consider like some long-term instance. For example, there's a substantial passenger behavior changes that may last more than 1 hour. Like for example, at the beginning of the day, probably say like one station get closed for like 1 or 2 hours, and people may have to choose a different routes. These are like what they call long-term instance. And we did some empirical analysis on how people's behavior changes in the system. And if you look at left-hand side, we say that during instant time, we can use the automatic fare collection data to quantify the passenger flow movements in the system, clearly seeing like how passengers start choosing nearby bus stations or nearby or transfer to nearby rail stations. And this empirical analysis support an automated impact analysis. And this will give a lot of data support to operators to understand, okay, where now under the instance where the system become much more busy, and how we could accommodate them. And another idea we want to think about is how we can infer passengers' response to the system. And in another study, we propose a probabilistic framework. The idea of using this probabilistic framework is because even if you observe some passenger transfer from a block station to nearby bus stations, you never know like whether he's actually transferred to the alternative route due to instance, or he just transferred it for a normal commute, like it's a normal routine every day. In our study, we propose a kind of conditional probability to quantify like what's the actual number of people who transfer due to instance, and we compare our probabilistic framework with some rule-based method in synthetic data, and actually our method can predict can infer the passenger response much well than the rule-based method. So these two support us to understand the impact of long-term incidents, but there are also a lot of short-term incidents in the system. Think about the short-term instance as some disturbances in the system with like less than 5 minutes. This can be like some behavior randomness of drivers, some signal disturbances, and some stop and go and traffic issues for buses. So in our like empirical analysis, we actually observe in Chicago transit system, more than 75 of the incidents are short-term incidents. So with this instance, we wish to propose a theoretical queuing analysis framework to quantify the impact on passengers' waiting time and passenger queue length at each station. And we also want to quantify the stability of the system. The stability means the system is unstable if the time goes to infinity and the queue goes to infinity. And we, after a series of theoretical analysis, we conclude the stability condition of the system. And this specific formulation, if you look at it in details, you will see like higher rate of instance and higher duration of each instance will make the system more likely to be unstable. It's a quite intuitive results. What does this closed form formulation means? It can be used to calculate the queue length and waiting time very efficiently, because compared to other simulation method, this theoretical closed form formulation gives you direct way to calculate the queue length, and especially when the queue length is under the stability margin, then your simulation probably cannot capture whether the queue length will go to infinity or not because of some randomness in your simulation or some approximation in your simulation. But this theoretical framework tells you exactly whether this design is stable or not. So this formula can also be used to diagnose your public transit design. Like for example, under current demand and headways and vehicle capacity, whether the passengers' queue length at the station will go to infinity or not, if we consider some frequency of instance and some mean duration of instance. Cool, these are our understanding work, and now we think about some controlling work. What can we really do during the public transit disruptions? Let's also think about some long-term disruptions, and passengers may have to choose a different route or wait there for like sometimes like 1 hour or 30 minutes to wait for the system to recover. And here we consider a specific strategy for control is path recommendation. And we observe like if we don't provide any guidance to passengers, most of the passengers will choose nearby bus routes as an alternative, especially some parallel bus routes. And this actually makes the bus route become much more congested than before, and some passengers may suffer from even more delays because they are not being able to board the bus. And so a more clear, a more smart way is to distribute passengers to different routes. And this is corresponding to path recommendation. Let's think about some passengers, they have an app. It's a kind of instant management system app. And in the app, if they input their origin and destination, we show there some recommendations. And let's assume if you only show one different recommendation, and passenger may or may not follow this recommendation because they have their own domain knowledge. In that case, passengers' behavior become uncertain. Let's look at the right-hand side graph. Every column is every recommendation of the system, but passengers' actual choice probability, which you look at in a row, every row, it actually will be affected by the system recommendation, but it may not necessarily be whichever the recommendation is, the passenger will follow. So in that case, passenger's behavior become a random variable because their actual path choice will be random, depending on the probability of which passenger will choose. And this probability is conditional on which recommendation the system provides. So with this randomness in consideration, the passenger behavior actually makes the passenger flow become a random variables. And passenger flow is one of the decision variables in our network in our network assignment model. This make it challenging to solving any like optimization model. And we propose new ideas to treat the decision variables as realizations. So from random variable to a deterministic variable, and we try to. But this kind of treatment is not like it's not equivalent. So we have to add some constant to make it somehow equivalent. So we add two constants called epsilon probability and gamma concentration. These are like two specific concepts with respect to some linear constants in like probability theories. And the good part is like we prove under these two constants we added, the new proposed like formulation with this kind of approximation has very good solution quality bound. The optimal system travel time on this new formulation is very close to the expected system travel time without approximation. This expected system travel time without approximation is a true system performance indicator. So if the epsilon and the gamma are small enough, we show the theoretical bound of the performance qualities. And we implement our method in Chicago. Also say like more than 6% decrease of average travel time in the whole system. And if you only look at incident line passengers, which are passengers being affected most, this will reduce their total travel time by like 19%. And the implementation, if you combine my several studies together, it potential to develop a management system where you have this real-time monitoring of the system's impact, incident impacts, and propose some reschedule plan or pass accommodation plan in real time, so that like everything is automatic. I also want to highlight one potential, like one unified framework and extensions of my current study. I'm talking about short-term, long-term instance, but there's actually no specific bound between them. It should be a continuous spectral for this different incident types, and it all depends on degree of behavior operational changes. And it can range from normal to short-term to long-term. And under this matrix, you can fit in a lot of different future studies. And my like thesis only part of it. Yeah, that's all my presentation.
Excellent. Thanks. Rounaq?
Yeah. Bhuvan, would you mind sharing your screen? Thank you. All right, so my dissertation looked at different strategies and the implications of coordinating accessibility improvements with housing policies in order to plan sustainable cities and achieve sustainable mobility outcomes in particular. Next slide, please. Although I don't need to belabor the need for exploring sustainable mobility pathways to this particular audience, I want to highlight two challenges of society's dependence on private automobiles that have been receiving attention in recent years. First, in response to the contribution of the transportation sector to the climate crisis, we are now looking more closely at ways to reduce greenhouse gas emissions from transportation, especially from light-duty vehicles, which are largely used in a single occupancy manner. At the same time, vulnerable road users like pedestrians and bicyclists are increasingly at risk while navigating public roads. In the US, which is one of the most auto-dependent settings in the world, road fatalities, as you can see, have remained abnormally high in comparison to peer countries and have unfortunately shown an increase in recent years. Next slide, please. Now, recognizing these challenges, many public agencies around the world are planning and operationalizing car light programs that are aimed at reducing private vehicle ownership use and emissions. But the key challenge we face is to do that without reducing mobility and accessibility for people using our transportation systems. Most car light programs adopt a carrot approach where they try to improve alternatives to private cars, such as better public transportation, using emerging mobility services like microtransit or micromobility, or better and safer facilities for pedestrians and bicyclists. Very few programs, on the other hand, take on the politically challenging idea of making owning and using a car less attractive through, let's say, road usage pricing or higher parking rates. Next slide, please. Through my dissertation, I was interested in exploring how people might react to these types of car light programs if they were to be piloted at a neighborhood scale within a city. How might these neighborhoods evolve over time as a result of the car light pilot implementation? One way to think about this is that better non-auto options would incentivize some people to reduce their car usage and perhaps even give up their car. The other, often ignored consequence could emerge through the housing market. Better non-auto options would increase the attractiveness of these neighborhoods, which would increase housing prices and attract higher income households who are usually reluctant to give up their cars or use transit, despite living close to transit. We've seen this play out many times before through transit-induced gentrification. So how might these two opposing forces interact with each other, and what would the net effect be? That's what I set out to explore in my dissertation. Next slide, please. I looked at 3 types of car light policies through scenario analysis. The first was a blanket ban on private vehicles, which some activists and some of my friends argue for. The second was an improvement in non-auto modes to the extent that the accessibility playing field would be leveled. And the third was a combination of non-auto accessibility improvements with 2 types of housing policies: upzoning, which is increasing housing supply within that neighborhood, and reducing vehicle ownership opportunities by restricting parking supply in the new housing units. Next slide, please. To do this sort of scenario analysis, I used an integrated urban modeling approach. In particular, I used SimMobility, which is an agent-based land use transport interaction, or a LUTI microsimulation model that we have developed at the Singapore MIT Alliance for Research and Technology, or SMART. SimMobility has different components where micro-level decisions about residential location, vehicle ownership, job location, and daily activity patterns are modeled. Naturally, the model was calibrated for Singapore, which is a much less auto-dependent context than the US, for instance. Over half of Singaporean households do not own any private vehicles and live car-free. Next slide, please. So what would a blanket ban on private vehicles look like? Well, as it turns out, even in transit-rich Singapore, banning private vehicles would hurt formerly vehicle-owning households. Their accessibility would reduce by almost 40% on average. And as a result of everyone starting to use public transport, without major system improvements, consumer surplus would decrease across the board, even for those who do not own vehicles. Next slide, please. Now, when I looked at how improving non-auto accessibility would play out, I found a disturbing occurrence. Lower income neighborhoods that also had lower vehicle ownership rates seemed to be much more susceptible to accessibility-induced gentrification. This is certainly not what car light policies are intended to do, but as we have seen with transit-induced gentrification, there are risks of unintended consequences without careful planning and coordination. Next slide, please. Naturally, the next question we must ask is, are there ways to mitigate these undesirable consequences while maximizing the benefits of accessibility improvements? I explored various coordinated housing and mobility policy combinations and found that it is really important to think about how these policies are operationalized. While there is no silver bullet through a one-size-fits-all policy, certain combinations can end up doing more harm than not intervening at all. Next slide, please. With that, I want to leave you with 2 key takeaways from my research. The first is to encourage a more holistic understanding of how urban systems interact with each other. As we saw, planning sustainable cities will require careful attention, not just to the transportation impacts, but also the housing and land use impacts of better mobility services and technologies. Next slide, please. Now, many of us in this forum grapple with figuring out ways to accelerate sustainable mobility outcomes on a daily basis. My second takeaway is a sobering thought. The solution, so to speak, is to embrace a carrot and stick approach. One without the other is likely to induce undesirable consequences and hurt communities, often those who are already disadvantaged. Thinking about how we might make this politically palatable and socially acceptable remains a challenge that we need to address soon because time is not on our side. Thank you.
Excellent. Thanks, Rounaq. Karthik?
Do you want to share screen, Karthik? I can stop sharing.
Yeah, I can share screen.
Sure. Yeah, you'll have more control.
Awesome. Thank you so much. I'm going to shift gears a little bit and move towards the air transportation side of things. And I think the air transportation system, it's no surprise to everyone that it's super critical in the world and it enables connectivity at unprecedented scales. So just to give a sense of how big the system is, like on a global scale, annually, 4.5 billion passengers use commercial air travel. What's often overlooked is that we also move $6.7 trillion worth of goods across 22,000 city pairs with about 40 million scheduled flights. But the real motivation for my thesis comes from the fact that the system is far from perfect. And flight delays is something we all experience that actually not only inconvenience us, but also is often expensive. And this problem is super prevalent. So at least in the US, this has been true for a long time now, over decades, that almost 20% of the flights end up with an arrival delay of more than 15 minutes, and 2% of the flights are canceled. So this costs the US at least $30 to $40 billion a year. And if you think about how much it costs per flight per minute of delay, that's almost $300. And this is excluding all the environmental impacts of the emissions as well, especially emissions at higher altitudes when flights are put in these holding patterns. So when I started out in 2014, I was under the impression that we should build the best aircraft and that solves the problem. And that's what engineers should do. And the last almost 8-9 years have been a realization that the problem doesn't end with energy efficient aircraft and new engines, but how we actually operate and use these aircrafts in the real world. And that can have significantly higher consequences than even a few percentage point improvements in aircraft performance. So if you look a little bit into what causes flight delays, often the root cause of most delays is bad weather, which leads to reduced capacities at airports, blocked airspaces. But then airlines don't operate just one flight per day with a given aircraft. Each aircraft often makes 3 to 4 different flights during a single day. So when you end up with delays induced on one of those legs, they often tend to propagate, right? So if you look at on a per delay event basis, almost 40% of the delayed flights are because the incoming aircraft was late. And this is something we have often experienced when we are at an airport, that the most common reason we hear why your flight is going to be late is that the incoming flight was delayed. And this is really the motivation for my thesis. The question that I sought out to answer is, how do we model the spread of these delays in the whole air transportation system? And the purpose of developing these models is to A, predict delay propagation better, but B, also come up with better techniques to control and reduce the spread of these delays. So this is not an entirely new problem per se, and there are a bunch of tools that we have used in the past to address this question. And one very simple approach that has been becoming more and more popular off late is to use data, right? So the advantage of data-driven methods is that they are often geared towards increasing the accuracy of their prediction, meaning you want to know very precisely whether your flight is going to be delayed even 3-4 hours in advance. But the con is that these are often black box models. So we don't tend to have good interpretability. And interpretability is important when you want to use these models to answer what if questions, right? So if I made an intervention and a new change in the system, I want to know whether this is actually going to reduce delays in the future. And data-driven methods are known to be poor when you deploy them in out-of-distribution settings, in distributions which are different from what they were trained on. The more analytical and principled way of thinking about this is to use queuing theory models or network models. They are very interpretable, they're analytically tractable in some cases, but the con is that they're often hard to calibrate with observed data. So they're not accurate in many settings. So my thesis sought out to get the best of both of these worlds, which is how do we merge the benefits of data-driven methods in terms of improving accuracy with the interpretability and analytical tractability that we get with these network models. So the key feature that I capture in the new model that I developed is just two observations. One is that delays at airports don't change abruptly. And this is simply because it takes a while for delays to get built up, because you want queues to get built up. There's often a line of aircrafts, as I show in this picture, with like flights waiting to take off. So these queues don't get built up super instantly. They often like could take something like the order of hours, which means they also don't go away super quickly. And the second feature that I capture in this model is what I mentioned, which is that delays are often propagated. So we want to be explicit about capturing these network effects. And what this results in is a very simple equation which lays the foundation for my model, which says something like the inbound delay at some airport I at time t+1 is some scalar function of the delays that you see at time t, multiplied by a coefficient alpha, which captures the fact that delays don't change abruptly. And then another term which is capturing the network effects. So the delay at airport I is a function of the delays that you see at connected airports j. So in this simple formulation, the challenge that we would face now is that a lot of these parameters are unknown. So these coefficients that capture persistence of delays, the coefficients that capture network effects, and even the network interaction keeps changing with time. And the real innovation in my work was in actually using data to learn these discrete time-varying network topologies, meaning the discrete modes in which delays propagate in the system, and all these coefficients that would actually help us make this model accurate. So just to give a very quick flavor of how the model looks like, this model is called the Markov jump linear system model. We learned discrete network topologies that capture different modes in which delays propagate in the system. But then the important thing is that this model is interpretable, because you can see a very high level representation. In this case, a cartoon with just 3 modes, but you actually do use more discrete networks to capture the state of the system. So these modes or these network topologies are learned from data, and then we have simple linear models for each of these modes, which are also learned from data. And then the transition from one of these modes to another is something that you can learn from historical data as well. So at a high level, this model lets us gain some interpretability while also leveraging historical flight delay data that we have to improve accuracy. And we showed with some reasonable degree of confidence that this model is not only qualitatively good, meaning in the left plot, you can see that the model captures typical trends that we see, meaning delays increase during the morning, peaks in the evening, and then reduces at night, but also quantitatively compare it against a few interpretable models like regression trees, linear regression, but also simple versions of neural networks with multi-layer perceptrons. So the purpose of building all of this model was a prediction, and I showed that in the previous slide that we are able to gain more predictive power than other interpretable models, but also actually identify what are strategies that we can use to minimize delays. And the two important findings that we had from the study was identifying which airports we should target for delay reduction strategies, and that's the figure on the left. And at least in the US, the answer is largely focused on Atlanta, Chicago, San Francisco, and Los Angeles. because for every minute of delays that you reduce at these airports, you're going to get the most system-wide benefits because these airports are super well connected to the whole system. There are a lot of flights going from these airports to other parts of the country. And the second is that the ideal time to reduce these delays would be somewhere between 10 a.m. to 2 p.m. Eastern. You don't want to start out too early in the morning because you're not sure if that day would end up with a lot of delays. You don't want to do it too late because at that point, delays have built up significantly. And like I said, delays tend to persist for a lot of time. So you might not get a lot of value if you intervene beyond 2 p.m. So in summary, I think this class of model called the Markov jump linear system model sort of helped us bridge data-driven methods with more analytical network models. And I think this is a pretty powerful framework which we can use to study other large-scale transportation systems. So we actually took this and have started using some versions of it to study a potentially more congested airspace scenario itself with more unmanned aircrafts and urban air mobility systems that are going to be developed in the future. But I also think that this model offers a lot of promise for us to study even problems in surface transportation, in particular predicting how road congestion propagates and how delays in some segments of the road can actually, or for instance, in some of these crucial tunnels that go into Manhattan could propagate into delays for other parts of the city. That's my presentation. Thanks, everyone.
Excellent. Thank you. Yeah. So, Bhuvan, if you don't mind, let's spotlight all three panelists on this. Yeah. So at the first round, I actually encouraged the three students to ask questions of each other. Maybe Rounaq, do you mind? I start with you, then Karthik, then Baichuan. Let's ask a question first and then respond depending on who is being targeted. Rounaq, please. Any comments or questions, please?
Sure. I really appreciate the work that both of you have done. It's really exciting to see that we are now able to use these sorts of methods and make use of the large volumes of data that we have. In particular, Karthik, I really appreciated that you're trying to bridge data-driven methods with interpretability. That's been a common critique in recent years of machine learning models in particular. So it was great to see that work. I have a question for Baichuan. So the method or the framework that you proposed helps public transit agencies be more responsive, be more agile in mitigating the effects of these disruptions. I was wondering if you have any thoughts about the effects of disruptions in general on public transit ridership, because I imagine there would be a tolerance threshold beyond which some folks might just stop using public transportation. So that behavioral element, I'd love to hear your comments on that. Yeah, I don't have any questions for Karthik.
Okay. Yeah, thanks for the question. Yeah, we did in our empirical analysis analyze the total demand change in public transits under long-term disruptions. There definitely will be a decrease in total demand. We also capture like how many people will just give up public transit. I don't remember specific numbers, but that is captured in our empirical analysis. What's our assumption? Like if it's a short-term one, we assume they are still waiting for the system, but long-term ones, there's an option for them to choose alternatives like nearby bus routes, still waiting public transportation systems, or like just to use other mode that is not in the system. Yeah, but they're all captured. We can use data to capture that as well.
Yeah, I think Rounaq, your question is if a system degrade to such an extent that people no longer see this as a one-time incident, as a general picture of the public transit, that will trigger a big kind of a drop in that. Thank you, Karthik.
Yeah, I had a question for both of you guys since you have more experience in the surface transportation space. One thing that I have been like at least interested in the last year or so is this question of equity surrounding electric vehicles. So electric vehicles, one of the major concerns people have is the issue of range anxiety. And a prerequisite to sort of address that is you have access to charging infrastructure, right? So it's either home charging or access to public charging network. So I was curious if what both of you think about like relating potentially your study, Rounaq, on equity and accessibility, and how that could help us guide EV infrastructure.
Yeah, I'm happy to go first, if that's okay. Well, I think we'll need a longer conversation to really dig deep into my thoughts on electric vehicles. But I will say that the rollout of EVs, as we've seen them over the past few years, has certainly not been equitable. The subsidies are being provided in a somewhat selective manner. The prices of EVs have not really come down to the extent that everyone can afford to purchase a private EV. Car sharing services could be one way to kind of bridge that gap with electric vehicles. There are a few startups in that space, but it's still not yet mainstream, so to speak. But also what I have observed is that the spotlight on EVs, both from a funding and policy perspective, is detracting from some of the other policy levers that we have at our disposal, like public transportation, walking and biking, parking, and land use, and so on. So I think we'll need to figure out where EVs fit into the broader mobility ecosystem, and we haven't reached that equilibrium yet.
Okay.
Yeah, I had a question for Rounaq and another question for Karthik. The question for Rounaq is like, yeah, it's great to see you have implement model and do a very strong case study in Singapore. I was wondering, how do you think about your model can be adapted to US context, where the population is much less dense, and the investment to increase the accessibility of other transportation mode or public transportation mode can be very large, but the usage probably will be very low. And yeah, how do you think about that trade-off?
Yeah, in the dissertation, I did look at such a context, which was similar to the US in the sense that it was much more auto-dependent, looked very different from Singapore. And what we observed there was that the value of an improvement in non-auto accessibility is much higher. Even for the same magnitude of improvement, people perceive it to be much more valuable because the baseline is so low to begin with. Because there aren't good options to a private vehicle in more auto-dependent contexts. So when we think about the implications of that, I think we have to broaden our perspectives and not just think about public transportation. Yes, public transportation is important, but in many places that are low density, the current service delivery model that we see in urban areas might not work. We'll have to think about other ways to improve accessibility. That could be through microtransit, that could be through other avenues like land use and so on. But more generally, I think we'll have to broaden the mobility landscape.
Yeah, and one more question for Karthik. Yeah, and for your your proposed market model, I can say the interpretability traditionally from like transition of delays. Like you can identify which airport probably like most valuable. But can you capture the factors where the delays come from? Like if we instead of from other delays and other factors like originated or organic factors that affected, like instead of like affected by other airports.
Yeah, I think there are many levels at which you can root cause delays, right? So like in one layer of abstraction, you can say, hey, delays are caused at San Francisco because there are delays at Denver and Seattle, for instance. That's one level of abstraction. That's sort of the level at which my model works. The next level of abstraction is, hey, there are delays now at San Francisco because 5 hours ago, there was a thunderstorm in New York, and that's what caused those delayed flights to go via Denver and then show up at San Francisco now like 6-7 hours later. So I think that's the second level of abstraction, and that gets closer to the root cause. So I think the second type of study is much harder to do. And I don't think we have a lot of tools now to actually go down till that resolution. I think what we can say, at least with my study, is sort of that first layer of root causing, which is if you have delays at an airport X, what is it mostly because? Is it because X was delayed at the previous time step, or because there are certain neighbors of X that are highly connected to it that were delayed at the previous time steps?
Thank you. Baichuan, you want?
No, I have no questions. Yeah.
Oh, yeah, Buma, for the audience question.
All right. Yeah, thank you all for the fascinating presentations. It's a lot of questions, so let me get right into it. First one, Rounaq. You mentioned the carrot and stick approach. Obviously, there are different societal, individual, and political costs of carrots versus the cost of a stick. And there were a couple of questions, that the current political environment is leaning way too much towards carrots, particularly given that the externalities of greenhouse gas, pollutions, basically the land use of the space that a car takes on the road is not correctly priced. So what specific recommendations, is there a tool that you have in your thesis which generates a sort of analysis of carrots versus cost of a carrot versus cost of a stick approach? And can we introduce more stick-based policies based on the recommendations that your thesis proposes?
Well, before I answer that, I just want to pose a question to the audience. Would you be willing to pay $15 every time you drove into downtown? If your answer is yes, then I think you'd be supportive of these sorts of stick-based policies. When we think about stick-based policies, there are two sides. It's easy to blame it on politicians and say there just isn't enough political will. But we as citizens, we as residents also are unwilling to be supportive of those policies. When we look at New York City, for example, they're the first city in the US to really think about congestion pricing, and they've gotten further than most of us can imagine to get, at least in the near future. There's a lot of public resistance. So it's a two-sided coin there. There needs to be public acceptance, which in turn is going to influence political will.
Thanks. One for Karthik. So Karthik, so actually Joe asked this question, past handling of network problems will lead to particular delays depending on the handling strategy. So your model was trained, on, recovery strategies that were done in the past, might not have been ideal, so how do you avoid this sort of data bias? And, in your model, given that, interpretability of these models is not well thought of right now. So just your thoughts on that. Yeah.
No, I think that's a perfectly valid criticism of any data-driven approach. There is some degree of biasing that's going to happen to the previous data sets that you used. But I think what we can control is the degree of bias, right? So a neural network model, for instance, purely trained on previous data, at least, has a much stronger bias to the training data than the sort of models I'm proposing. So I'm just reducing the reliance of the past data by some extent over very highly data, overfitting style models. So I think at the other end, there would be models that are much more mechanistic than what I am suggesting. Like you can literally track queues of flights happening through the entire system, and that would reduce the reliance on past data. I think as you move towards more and more analytical models, you lose accuracy, and typically when we gain accuracy, we are losing interpretability. So I'm just saying maybe there are reasonable middle ground models that we can work with, and mine would be something that tries to make a step in that direction. But yes, there is a caveat on some data biasing, nevertheless.
Thanks for that. Baichuan, so this one's for you. So a couple of questions, on how the supply side uncertainty can be modeled, and whether it is reasonable to think that this becomes more important as we move towards, monitoring to control and planning, longer term changes to the system. So.
This is actually a great question. We didn't consider supply uncertainties in my thesis, but there's a couple of uncertainties that I think probably can be considered. One is the incident duration itself. This definitely depend on infrastructure. And another is availability of alternative routes. like whether the shuttle bus design probably will be depend on like what's the availability of buses and operators in transit. And these are all suffer from uncertainties. You probably don't have enough driver probably will be absent, or the number of available driver probably will be like not certain. We didn't capture that in our study, but this definitely can be an extension of our like future research, especially for some control tasks. But what we did capture is something related to incident duration. We actually observe it can be simply extended to stochastic optimization. So if you just take the expectation of different scenarios, like incident scenarios, and I guess some supply uncertainty can also be captured in just consider discrete scenarios and using typical stochastic optimization. But yeah, this can be extension.
All right, thank you. Rounaq, so a very specific question. So you mentioned you use sim mobility tool. So does that have an option for including the mobility needs of people with impairments, accessibility issues in your models and your solutions? How did you overcome that sort of hurdle if it doesn't?
We certainly have the capability of modeling behavioral differences across different groups of people, as well as creating network or modeling network infrastructure that may or may not have capabilities of catering to folks with mobility disabilities, but we did not do that. We can do that, but we simply at the time did not have access to that data. The model was calibrated for 2012, and we simply didn't have access to that sort of nuanced data. All right,
thank you. Karthik, one for you. So you mentioned that one of the outputs of your model, is this ideal time to reduce delay at these, 5 airports: Chicago, LA, San Francisco, Atlanta, if I remember correctly. But how much control does one actually have, from a practical point of view? Like you're in an airport, it's 12 noon. So do you actually have this ability to control delay at a particular time? Can you just, for the benefits of the audience here, explain that? Because, there's a different cost for a different cause, for the delay. So how does that come into your calculations, and also the control aspect of a problem?
Right. So I think there are largely two ways in which we can intervene. One is at the airline level. Airlines do have reserve capacity. So they have spare aircraft, they have spare crews, reserve crews. So that is at a strategic level. You can plan where you position your reserve capacity. At the more tactical level, meaning at the time scale of 15 minutes or so, often when you want to delay a flight, you can, so think of Boston, right? You can only land 10 aircrafts instead of 30 typically. So now the question is, which of the 10 do you prioritize, right? There's going to be bad weather. So the way I choose which aircrafts I prioritize determines where I actually spread the delay. If I prioritize flights from New York, then delays are going to be lesser at New York versus prioritizing flights from, say, Buffalo, right? So I think that's a tactical lever that's used today to a great extent by the FAA. These are called traffic management initiatives or ground delay programs, and they often tend to have a priority ordering of where we actually transfer the delay. Now, the only question there is centered around equity. Are you equitable in spreading the delays, or should you actually be efficient to minimize the system-wide impact?
So keep that in mind as you book your holiday travel tickets, folks. I hand it over to you since we have only 2 minutes left.
Yeah, wonderful. Thanks so much. Yeah. So Professor Dan Roos and Eva Roos actually with us today. I will invite Dan and Eva to say a few words. I should say that Dan and Eva not only generously support this Dan Roos Prize, the whole MIT Mobility Initiative is very much a thanks to Dan's effort for really kind of cultivate the idea and supporting this whole organization all along the year. So thank you, Dan and Eva. Dan, please.
Well, I would like to thank the three presenters. And I must say, I am very glad I was not on the selection committee, because I would have found it very difficult to decide who won and who came in for honorable mention. All three of them were terrific presentations. The other thing I would like to do for the audience, for those students who are graduate students, to really encourage you to go for a PhD. I have not seen a situation in transportation and mobility that so needed good research done in order of making sure that we get good decisions made. If you just think of what's been going on in the last week. I mean, you've got the climate change conference in Dubai trying to decide, should you limit or eliminate fossil fuel? You have significant international tensions playing out between the US and China with regard to EVs and deciding what the requirements are for consumers to get a $7,500 credit, and to what extent are we going to encourage or limit the use of Chinese technology in our EVs, where China has a technological advantage. We had the shutting down of one of the two biggest autonomous vehicle services, with the CEO fired, with a big hit to General Motors. We've already mentioned here a few minutes ago what was going on with regard to New York City and congestion pricing and some of the issues in New Jersey. All of these, by the way, are in the New York Times and Wall Street Journal. I mean, they're not just in professional journals. And so the point I really would like to make is that we need you all to go get your PhDs, hopefully at MIT, and to make sure that decisions are going to be made so we can get better decisions made in terms of the implementation of these ideas. They depend very much on your research. So thank you all very much.
Well, that's brilliant. Thank you, Dan, for the encouragement. I hope this year actually will get to the applicant number doubles with your remark on that. We're at time now. So thank Eva and Dan again for the generous contribution. And everybody, please join me congratulate to Karthik, Baichuan, and Rounaq for the winning this year's award. Thank you so much.